All right, we're going to start doing some calculations with the Doppler shift equation. So I need you to have your notes out, get a calculator out, and I want to just do a sample problem for you before you try a couple on your own. Okay, so first off, it's a very simple relationship. If you can measure the change in wavelength compared to the expected wavelength for any wave from a source that's moving relative to the observer, you can figure out the velocity of that object. And here's the argument. If an object is moving and it's emitting some light or some sound, some kind of wave energy, then when it's received at a different wavelength than it's expected because of the motion, because of the velocity. The greater the velocity, the greater the change in wavelength. If there's zero velocity, if the object's not moving relative to the observer, then we know 0 divided by anything is 0. It would be 0 change in wavelength. So this is only if there's some relative motion between the source of the wave and the observer. So here's what we'll do. First, identify the change in the wavelength. The wavelength we observe that's shifted minus the expected wavelength that's unshifted, and divided by the expected wavelength that's unshifted. That ratio is equal to the ratio of the velocity of the object that's moving, emitting that wave, compared to the velocity of that wave energy. We started looking at sound waves moving at 340 meters per second on average in air, but now we're going to look at light waves, and light waves move at the speed of light c. That's the constant that we've measured, about 3 times 10 to the 8th meters per second. So this equation becomes a little easier because we're going to assume the velocity of a light wave is a constant. It doesn't matter what light, all light waves travel at that same speed. So all we have to know are the two wavelengths, what's expected, and compare that to what we observe. So let's pretend we have this sample hypothetical problem. An expected wavelength of hydrogen light is known in its light spectra to be at about 655 nanometers. The same light spectra is observed at 657 nanometers from the Sombrero galaxy. What does this information tell us about the Sombrero galaxy? So immediately, you can identify that the expected wavelength and the observed wavelength are different. There is a change in wavelength, therefore the object is moving relative to Earth, relative to us on Earth observing it. So is this a red shift or a blue shift? Well, as the wavelengths get larger, they move towards the red end. As they get smaller, they move towards the blue end. So this would be a red shift. This is what's known as a red shift. It doesn't mean the galaxy is turning red. It just means that the spectral lines that we observe are shifted to longer wavelengths, when red is longer than blue, hence the term red. So does this mean the object is moving towards us or away from Earth, where we are observing? Well, if the lengths are getting bigger, that means the distance between us is getting greater. It's stretching. So we know that this is away. A redshift means it's moving away. So now we have some information. Now the question is, well, how fast? How fast away? Substitute it into the formula, and we can figure this out. We have a 657 minus 655 divided by the expected wavelength of 655. These are units of nanometers, and whichever unit you use, whether it's a nanometer or not, as long as they're the same, they cancel out. So the units are gone, and you're left with the units of velocity. In this case, the unknown velocity v, which we don't know, divided by the speed of light, 3 times 10 to the 8th meters per second. And to solve for this, if we know the speed of light, you can enter that as 3e8 on your calculator in units of meters per second. Just simply multiply that across, and you will have your answer. So the difference is 2 divided by 655. That ratio cross-multiplied by 3e8 gives us the recessional velocity of this object we're observing. Substitute those values into your calculator. And we get about, I'll just round this to 3 digits, 916,000 units of meters per second relative to us. This is a positive number because it's moving away. If the difference gets larger, you'll always get a positive velocity, which means it's redshifting, moving away. If the difference is smaller, you'll get a negative velocity, which just tells you the direction, which would be moving towards Earth, or a blue shift. Okay, try to apply the same formula to the next problems in your assignment.